Hi. So then you've seen so far that matrix products don't work out terribly well. They don't have a lot of nice properties. But for certain kinds of matrices, we can actually simplify things a little bit. In particular, what we call upper or lower triangular matrices. Multiplying them together, you get a really nice result. So we say that a square matrix is called upper triangular if all the entries below the main diagonal are zero. It's called lower triangular if everything above the main diagonal is zero. So think of it as if it's upper triangular, all the information is on the main diagonal or above. Everything else is zero. Now, symbolically, we say that something is upper triangular if a sub ij is zero, if I is more than j. In other words, if you are looking at a location, ith, jth, and you have a row index is more than the column index, well, then you're below the main diagonal. That means that entry has to be zero. All these matrices you see right here, these are all upper triangular. And the way we often kind of show people that is to draw like a little triangle. So then, for example, this guy right here is upper triangular. This one right here is upper triangular. This guy right here is upper triangular because all the entries below the main diagonal is zero. Actually, the last one is also lower triangular. It's lower triangular because everything above the main diagonal is zero. Notice to be upper or lower triangular, we don't care about the diagonal at all. So on the diagonal, entries might be zero or not. We don't care. So again, upper triangular, everything below the main diagonal is zero. Lower triangular, everything above the main diagonal is zero. It winds up being that if you ever multiply two upper triangular matrices of the exact same size, the result is always upper triangular. And I can even say more. So if you take the product of two upper triangular matrices of the right size, same size, you will get an upper triangular matrix. And the entries on the main diagonal are also easy to find. You just take the corresponding entries on the main diagonal in the factors in the product and just multiply them together. That would then be the main diagonal for your product. The same is true for lower triangular. If you take a product of two lower triangular matrices, it'll be lower triangular. To go and show you actually how to use it, I'll do it a few times and then I'll prove it to you. Often this one's a little tough, but I'll prove it to you because it's important to see how this stuff is done. So as an example, notice that the first matrix is upper triangular. The second matrix is upper triangular. You can see then upper triangular, upper triangular. So the result then is going to be upper triangular. Right away, this is going to be zero. It's upper triangular. But then the entries on the main diagonal for the product is found by taking the corresponding entries on the main diagonal of the two factors in the product and just multiplying them together. So 2 times 1, that's 2. 2 times -2, that's -4. That's great, right? That makes finding the product of two upper triangular matrices, it makes it pretty fast. This last entry, though, we still have to do the column row, or in this case, sorry, row column form. So go ahead and take this row and multiply it to take the dot product with that column. You would then get -5. That's the answer. That's that multiplication. This next example is the product of two lower triangular matrices. Lower triangular because everything above main diagonal is zero. So the answer has got to be lower triangular. So then this must be zero. The entries on the main diagonal are easily found. You just multiply the corresponding entries on the main diagonals of the two matrices in the product. That would then be 12 and -2. It's great, right? And the last one, you have to multiply that out. So then this would then be the second row and the first column to find the first row, second row, first column of the product. So that would then be 5. And that's the product. The last one, notice that this is upper triangular. It's upper triangular. But it's also lower triangular. That means that both facts I just gave you are true. So the result then is upper and lower triangular, which means it's a scalar matrix. So you have 0, 0, 0. You'd have a 0, a 0, and a 0. And only the entries on the main diagonal you have to worry about. But to find the entries on the main diagonal, you just multiply corresponding entries. So then here, this would then be a 3, a 2, and a 10. That's it. That's great, right? It makes multiplying scalar matrices Oh, really easy. To multiply two scalar matrices like I just did, all you do is get another scalar matrix and you just multiply the entries on the main diagonal. It's great. Okay, good. So now we'll get into the tough one, which is you really need to see why it's true. So let's go through it really slowly. Let's say you have two matrices that are both the same size, they're both square, and they're both upper triangular matrices. I'm going to look at the ith-jth entry of that matrix. I will look at it where I is more than j, so that means below the main diagonal, or I equals j, that is the main diagonal. Okay, so I'm going to look at the ith-jth entry where I is at least as large as j. So that means if it's more than it, we're looking below the main diagonal. If it's equal to it, then we're actually on the main diagonal. So then just by doing the matrix multiplication, the ith-jth entry of the matrix A times B can be expanded out by using this notation. That's just doing the dot product where I have emphasized certain parts of it. You're feel free to sit down and look at it and try to write it out yourself. Next, consider some cases. Since A is upper triangular, then every single A sub I sub K, IK, that's going to be 0 if I is more than K. So in the first set of parentheses, this guy right here, notice that this is more than that. And this is more than, oh, not that one. And this is more than that, because at the end here, I have this is certainly more than that. So I'm assuming then, the way I've written it, that I is more than all those numbers. So I can replace all those A sub somethings as zeros. So this whole mess, all of that is equal to all of this, and that's just 0. So I now know all of this vanishes and goes to 0. Look at the second grouping I've made for you. Here, similarly, because B is upper triangular, then B sub Kj is going to be 0 whenever K is more than J, because that's the definition of what it means to be upper triangular. But then since I is more than J, that means that since I is more than J, then this is more than that. So this guy is 0. You can use that argument then all the way down because this never changes. See, that's a J. That never changes. But this part becomes larger and larger and larger. So this N is more than J. So then this is 0. So that summation of products is equal to this summation of products, and that's 0. That means this second grouping is also 0. The only thing left is that one term I left out behind. The one term I left behind. So we have then that the ith-jth entry of AB, where I is more than J, at best is going to equal to what I just wrote down there. It's equal to that thing only, just that one thing. That's all it could be, if anything. It's the only thing it could be is that thing. But now consider cases. What if I is equal to J? What if I is just strictly more than J? Because I assume that I is at least J. So if I is more than J, well, then it's 0. Because then if I is more than J, that's 0. Because B is an upper triangular matrix. And anytime the row index is more than the column index, that's 0. So that's 0. If I equals J, that means we're on the main diagonal, then the ith entry of that product is found by taking the entries on the main diagonal, the two separate matrices, and just multiplying them together. And that's it. That explains why it's true. So this then shows you symbolically why a product of two upper triangular matrices is an upper triangular matrix, but then also why that the entries on the main diagonal are easily found by just multiplying the corresponding main diagonal entries of the separate two matrices. Good. So the last few things. So I also introduced to you the object or the operation of transpose. There are operations or algebraic properties of transpose that are true. I, though, don't really want to go and prove them all. I've already done enough proofs. You've seen they've been pretty intense. So I want to focus just on how to use them quickly. So many of these are very self-evident. So if you take A transpose and transpose, you have to get the original matrix back, because transpose means to flip it around the main diagonal. So transpose means to flip it and then flip it. You get right back to where you were, of course. So if you take A plus B and take its transpose, that's the same as taking A transpose plus B transpose. That's because if you take A plus B and add them and then take its transpose, you flip it. So then you could instead take A and flip it and take B and flip it and then add those flips. That's what it says. So those two are pretty obvious. The scalar times A transpose would then be K times A transpose, because the K comes out of the scalar multiplication anyway. The only one actually that are confusing for people is A times B transpose is not A transpose times B transpose. Once again, matrix multiplication causes problems. It's because of the way we set things up, because we wanted to make sure that matrix multiplication in some way has linear combinations built into it in some meaningful way to make it easier to understand how we use matrix multiplication in applications later. So A times B transpose is actually B transpose times A transpose. If you want to see a proof, the proof is in the book. It's not very difficult at all. It's very similar to things I've already done, but it's more important right now to just go and do it. One thing, though, it is true is if you take A to an integer power and take its transpose, it's actually the same as taking the transpose first and then taking the result to a power. That's nice that those two operations actually do reverse each other. To show you how this can be used, most of the time, these properties are used really only for algebra. Really, it's just used for algebraic properties. You won't say, okay, here's your matrix with numbers, and then take its transpose, and then take its transpose again. Like, you would never do those operations. You would not literally write that down. You would know that A transpose is just A. So to show you how it's really used, I'm going to show you that if you take any matrix, I don't care what it is, it could be any size now. It doesn't even have to be square. If you take any matrix and you multiply it to its A transpose, the result is always symmetric. The reason is very straightforward. It's just a matter of looking at the operations. So then, as a quick proof, suppose that A is a M by N matrix. So it could be any kind of matrix now, not just square. Then A transpose is N by M. So A times A transpose is a M by M matrix. This is important because, you see, to be called a symmetric matrix, it must be square. So the number of rows has equal to the number of columns. So I had to show you that the number of rows and the number of columns are both M if the original matrix is M by N. Now, to show it's symmetric, I have to show that if you take its transpose, you get the same thing back. So let's just do that. Also, if you take A transpose and take its transpose, let's see what happens. You know that when you take a transpose of a product, you reverse the order of the product and take the transpose of the factors. So I reverse the order of the factors, and then I take the transpose of what's left over. That's one of the properties. But another one of the properties is that A transpose is just A. So that's A times A transpose. Notice, so A transpose is symmetric by definition, because the matrix A transpose, that product, its transpose is itself. That's it. So you can use this exact same argument, by the way, to show that if you take a matrix, a square matrix now, this time it has to be square. You take a square matrix and you add to it its transpose, the sum A plus A transpose is actually always symmetric. Now you might wonder, this sounds like a semantics. Why do we care? Why do I even care what's symmetric and what's not? It winds up being that symmetric matrices have an insanely important property that you won't learn for quite some time. So knowing when things are symmetric or not is super useful for applications. So then you will not very often use these properties outside algebra. You just won't. You'll use it to look at it ahead of time and go, oh, that matrix is symmetric. That means I can do this really cool thing with it. You just don't know the really cool thing yet. And I believe that that's enough for this video.